All right, for homework number 2, we are just kind of running through a lot of our different integration techniques that we've learned so far. So it just says find the indefinite integral. So you should be thinking for each one, I always start with like, does u sub work? And if u sub doesn't work, then the next question is maybe it's either a trig identity or maybe it's one of those inverse trig integrals. So, okay, so looking at this first one, u would be t minus 8 du dt. Make this a little bit bigger. There we go. Du dt would be just 1. So in place of dt, I can just put du. And this is going to be u squared, and the 9 can get pulled out in front. So this can be 9 times the integral of 1 over u squared, or u to the negative 2, du. And then to integrate that, you add 1 to your exponent, so this becomes u to the negative 1 divided by negative 1. There's a plus c there. I started doing definite integration and then realized we don't have any, this is not a definite integral. And then I'm just going to rewrite this and sub in my expression for u. So let's make this negative 9 over t minus 8 plus c. You could also, if you don't want negative 9 over t minus 8, I think on my answer key, I distributed the negative through and made it 9 over 8 minus t plus c. It doesn't matter. You do need to know that those are equivalent. Okay, for the next one, again, u sub would be setting the denominator or the larger degree item equal to u. And so du dt would equal negative 3t squared plus 9. We have t squared minus 3. Now, you can factor a negative 3 out of this. Negative 3 t squared minus 3. So all we need to do, sorry, hold on. Let me work on this a little bit. So du, it could be this times dt, and then we can just divide this over. Or you can say, oh, all I need is I need a negative 3 in here, so I'm going to balance it out with a negative 1/3. However you want to do that. I think we've been doing this solve for dt thing. So I'll try to keep it consistent. This is the most straightforward approach. Solve for the dt so you can replace the dt with your expression. And then see how I have the 1/3. I have the negative 1/3 in here. The t squared minus 3 is going to cancel. So now this is negative 1/3 times the integral of 1 over u du. And so that is negative 1/3 times the natural log of the absolute value of u, which was this expression, plus c. All right, next one. Now, u sub isn't going to work here with x squared, with u being x minus 1, because x squared is higher degree. And if we let u be x squared, then we're not going to get the x minus 1 to cancel out. So anytime you're top heavy by 1 degree, you should use division to separate this out. We haven't talked about, well, no, it doesn't apply. So for this one, you're not allowed to just like separate. Remember, this is like upside down heart. That's illegal to do. But you can say, let's divide x minus 1 into x squared, and I'm going to use my placeholders here, and just rewrite the problem. So x goes into x squared. You can put that in x times. That gives you x squared minus x. Subtract the quantity. So now this becomes 0 plus x. Drop down the 0. X can get multiplied by 1 to get x. X minus x is 0. 0 plus 1 is 1. The remainder matters here because what we're saying is instead of x squared over x minus 1, we can make this x plus 1 over x minus 1. And that's something we can integrate. You can integrate x, you can integrate 1, and you can integrate 1 over x minus 1. All right, so the integral of x is x squared over 2. The integral of 1 is plus x. And technically there's a little u sub happening here, but we don't necessarily need to show it because du dx is just 1. So there's not really any exciting I don't need any adjustments to make to satisfy u sub, so I can just go ahead and say plus natural log of the absolute value of x minus 1. And I know there's no extra coefficient or anything there. And then plus c because these are indefinite integrals. For number 25, when you have e's in the top and the bottom of the fraction, we want to default. Remember, the derivative of e to the x is e to the x, so we want to default to making the denominator u. So this is going to be u equals 1 plus e to the x. That means du dx would equal e to the x. And so du divided by e to the x would equal dx. So instead of dx, we have du divided by e to the x. The e to the x's can cancel. This is u. So now it's just the integral of 1 over u du. And that's nice and easy. That's the natural log of the absolute value of 1 plus e to the x. This is always positive, by the way, so we don't really need the absolute value, but I'm just going to leave it, plus c. I point that out because, I don't know, maybe they won't have absolute value in the multiple choices, and you might be wondering why it's not there. Okay, so 31. So we have trig here, and you should be thinking anytime you see trig, like, is this the derivative of something? Is cosecant, cotangent the derivative of something? Remember, the derivative, put a u in here, sorry. The derivative of cosecant is equal to cosecant u cotangent u. So this is the derivative of something. We still need to look. We still need to look at u sub though, because this is not just x in here. So there's going to be a coefficient involved. So u is pi x. Du dx is just pi. So du divided by pi is dx. So instead of dx, we're going to have du divided by pi. So that means that we should have a 1 over pi times the integral of cosecant u cotangent u du. And, oh, I think I did that derivative wrong. That derivative was negative. So because the derivative, let me write that correctly. The derivative of cosecant x is negative cosecant x cotangent x. So because there's no negative here, we're going to, when we integrate, we're going to get a negative. This is equal to negative cosecant x. Not x, though, u. Plus c. And then I'm just going to clean this up. So negative 1 over pi cosecant of pi x plus c. So remember, like when we have the integral of sine, that's actually equal to negative cosine, not just cosine. So sorry about that. Okay, and then 39. For this one, let's see. If I try to do some u sub, I kind of run into a problem because I guess I could split this up and do the integral of secant plus the integral of tangent, but integral of secant is one of those tricky ones that I don't know offhand, one of the natural log ones. And I don't think that they would have that version in a multiple choice problem. If I try to just let u equal cosine, then I have this issue with like 1 plus sine. So when you're kind of stuck like this, we had trig identities where we started with this and we tried to end up with something else. And the trick when we did trig identities was to multiply by the conjugate. That should sound familiar from your pre-calc days. Multiply by the conjugate to see if you can get something more workable. So 1 plus sine times 1 minus sine is 1 minus sine squared x, which should be jumping out at you. It's one of our rearranged Pythagoreans. And then when we did these proofs, we didn't actually distribute the cosine and the 1 minus sine. And the reason I'm doing this is because I can get 1 minus sine squared is cosine squared. And this, oh, there should be dx's here, sorry. And this cosine can cancel with one of these. So it doesn't look like I did much, but now I have the single term on top and the binomial is now on the bottom. And the good thing about that is it's kind of now like this E problem where we can let the denominator equal U because du will just, the one will just drop off. It'll be 0. So same thing here. I can say, okay, now U is equal to 1 minus sine. And du dx is now just equal to negative cosine x. And I have cosine x dx. I just need a negative in there. Or you could say du divided by negative cosine x is dx. So in place of this dx, we're going to have du divided by negative cosine x. So that gets the cosines to cancel. Don't lose the negative. So now it's negative integral 1 over u du. And again, why did I go through all of that? I guess I didn't show it, but if I let u equal cosine x, then I run into a problem with the u sub because 1 plus sine x, the derivative of cosine x is negative sine x, and that's not going to fix the 1. So this is not the only way to do this integral. Like I said, I could have used the secant plus tangent and gone from there. But I think this is the way that we would probably find one in multiple choice. So this becomes negative natural log of the absolute value of 1 minus sine x plus c. It's always a little tricky when there's trig, but I know we have done this exact trig proof multiple times in pre-calculus, so hopefully it looked a little bit familiar. All right, slope fields. In part A, sketch 2 approximate solutions of the differential equation on the slope field, one of which passes through the given point. So here's the equation for ds dt. The point 0, negative 1/2 is right here. So if I were to sketch the solution that goes through that on this slope field, you just kind of follow the tangent lines. Oh, I'm doing a bad job of that. And remember, on slope fields, we don't put arrows. I'm not sure. I think maybe this should come up here. We don't put arrows indicating it goes on because we only have the snapshot. And then actually, I think I'm going to erase that vertical part. Those are vertical asymptotes, so yeah, we're not going to draw that. And then just draw one anywhere else. So it doesn't matter where you put your other point. I put one here. So that would look something like this. So that's part A. Part B, use integration to find the particular solution of the differential equation and use a graphing utility to graph the solution. Compare the result with sketches in part A. Okay, so we need to integrate. First, we need to separate. So ds over dt. So it's going to be dt gets swung over here. So it's going to be the integral of ds equals the integral of t over 1 minus square root of 1 minus t to the 4th dt. All right, left side is easy. It's s equals. The right side, so this u sub is not going to work because there's more than a 1 degree difference. The derivative of 1 minus t to the 4th will be negative 4t to the 3rd, and that's not going to help up here. But this is inverse trig, where a is 1, u squared is t to the 4th, so u is t squared. And that works because then du dt would be 2t. So du divided by 2t is dt. And that's helpful because this dt gets replaced with a du divided by 2t. And those t's are going to cancel. So we have, I'm going to pull a 1/2 out. We have the integral of 1 over the square root of a squared minus u squared du. And that's arc sine. So arc sine, there's no 1 over a out in front. It's just arc sine of u over a. U is t squared, a was 1, so t squared. And then plus c. Okay, so that's our general solution. We want the particular solution. So we need to use the point that they gave us, which was 0, negative 1/2. So if I put in negative 1/2 for s, and I put in 0 for t, That's going to help me solve for C. The arc sine of 0 is 0. Remember, that's saying sine of what angle is 0. So that's 0. So C is just negative 1/2. And so that means that my function, I'm going to put it over here, is S equals 1/2 arc sine of t squared minus 1/2. And then confirm with a graphing calculator. I should see something that looks kind of like what I had here. And yeah, to graph any of the inverse trig, remember you would just do, so 1/2 second sine is arc sine of x squared minus 1/2. And then for the window, I'm going to match the window in the slope field. So it's -1 to 1. I don't really care what it counts by, I guess 0.5. Same thing on the y's. And that's how I got that graph to show up. Okay, number 54. So first draw one that goes through 0, 0. So here's that. So something like this. And then draw a second curve anywhere else. So I think I put one down here just for fun. Okay, and then part B, separate, integrate, celebrate. So integral of dy equals integral of tangent squared 2x dx. Is tangent squared the derivative of anything? No. Secant squared is, right? The derivative of tangent is secant squared. But if this is not the derivative of anything, then we need to use some trig proofs, or trig identities, excuse me, to work this out. So what is tangent squared equal to? It's equal to, let's see, tangent squared plus 1 is equal to secant squared. That's a Pythagorean identity that you have to know. So it's equal to secant squared of 2x minus 1 dx. And this is something I can integrate because secant squared is the derivative of tangent, and I can integrate 1. Excuse me. So we need a little u sub here. So for the integral of secant squared, let's separate this out a bit. I want it to be secant squared of u du. So what do I have to do to make that happen? Minus the integral of dx. So I'm only u subbing this first part. U is 2x. Du dx is 2. Du divided by 2 is dx. So in order for this du to be here, there must have been a 1/2, or du divided by 2, in replacement of that x there. Okay, so then this becomes 1/2. The integral of secant squared is tangent of u, which was 2x, minus, what's the integral of dx? X plus c. Now, if I had kept this all together and done u sub here, I think I would get the wrong c value because, again, you don't need u sub for the second term. You only need it for the first. All right, so then we're plugging in 0, 0. So use 0, 0. So 0 is equal to 1/2 tangent of 0 minus 0 plus c. Tangent of 0 is 0. So it looks to me like c is 0. And so my final equation is y equals 1/2 tangent of 2x minus x, and there's just no plus c. I graphed that. I'm not going to take the time to do that now, but I graphed that, and that matches what the slope field graph kind of looks like through 0, 0. So good. Solve the differential equation. All right, so remember, anytime I see y prime, I like to rewrite that. That's dy dx because it reminds me to separate and integrate. So if I'm looking at this, how can I separate? Well, I can multiply dx over. So 4 plus tangent squared x dy is equal to secant squared x dx. And then I need to get this x expression over here too. So I'm going to divide. So secant squared x divided by 4 plus tangent squared x dx. This looks kind of ugly at first, right? Except, because remember, we can't just make, if we just make u equal to 4 plus tangent squared, the derivative of tangent squared is not going to be canceled out up here. It would be 2 tangent secant squared. So this is inverse trig. Anytime you see a sum of squares, think about inverse trig. A squared is 4, so a is 2. U squared is tangent squared. And, oops, so that means u is tangent. And then we would need du dx, and that's secant squared x. So that's great because we have that, and we're going to cancel that out. Du divided by secant squared x will equal dx. So in place of this dx, I can put in a du over secant squared x. So the secant squareds can cancel. So let's rewrite this. Y equals the integral of 1 over a squared plus u squared du. And that's arctangent. So the arctangent is 1 over a, so 1 over 2. Arctangent of u over a, tangent x over 2 was a, plus c. We're supposed to be plugging in, oh no, we're not, just solve the differential equation. So that's it. They don't give us an initial point. So this is my solution to this differential equation. Now, arctangent of tangent, can those cancel each other out? I don't think so because it's divided by 2. So I'm not going to mess with simplifying that. Evaluate the definite integral. Use the integration capabilities of a graphing utility to verify your result. Now on this one, normally we let denominators equal u, but remember the derivative of natural log is 1 over x. So if we let u equal the numerator this time, du dx will equal negative 1 over x. So negative x times du will equal dx. Negative x du. So those x's are going to cancel. So it's negative integral from 1 to e of just u du. And that's negative u squared, but instead of u, I'm going to put this in. 1 minus ln x squared over 2 from 1 to e. So plug e in. The natural log of e is equal to 1. So 1 minus 1 squared is 0. Minus the natural log of 1 is 0. So 1 minus 0 squared over 2 is 1/2. So I'm getting positive 1/2. And when I typed this thing into my calculator, it agreed with me and also got 1/2. Okay, last problem. Find the area of the region. So it's hard to see, but this region goes from 0 to 5. And we should just be integrating, right? So this is the integral from 0 to 5 of 3x plus 2 over x squared plus 9 dx. I see a fraction that's bottom heavy by 1 degree, so I'm going to try some u sub here. I think it ought to work out, but we'll see. So, oh, actually, no, it's not going to work out. If I just do straight u sub, the plus 2 gets in the way, right? If I just let u equal x squared plus 9, then du dx is just 2x, and then what about the plus 2? So what we've done in the past is break this up. So 3x over x squared plus 9 dx, and then do a whole different integral. 2 over x squared plus 9. All right, so this u sub is still useful for this first one here. So du divided by 2x will equal dx. So in place of dx, we're getting du over 2x. So the x's cancel. That means we have 3 over 2 times the integral from 0 to 5 of 1 over u du. And then what about here? U sub is not going to work because there's no x in the top. So again, this is inverse trig, where a is 3. And instead of u, I'm going to use like w. A is 3, w is x. dw dx would be 1. So this is plus 2 times the integral from 0 to 5 of 1 over a squared plus u squared du. So the first one is 3 over 2 times the natural log of the absolute value of x squared plus 9. Evaluated from 5 to 0. And the next one will be plus 2 times 1 over 3, 1 over a, arctan of u over a, x over 3, from 0 to 5. And then I'm not going to simplify this very much, I don't think, but this is going to be 3 halves times the natural log of 5 squared plus 9. So 25 plus 9 is 34, minus the natural log of 0 plus 9, plus, I'm going to pull this 1/3 out, 2/3, times the arctangent of 5/3, minus the arctangent of 0, which is just 0. I would not simplify that. You could condense the natural logs a little bit. We would need a calculator for this next part, for the arctangent part. So I'm just going to leave that as is. All right, so that's homework number 2. If you're having trouble knowing which method to use, part of studying for this or prepping yourself for chapter 8 is to go back and make note of what the problem looked like and then what you had to do. So, and that might require a lot of writing. We have a lot of different problems, but as I've been talking through it, I've said, oh, because it looks like this, I'm going to do this. So that's something worth doing if you're really struggling on where to start for any of these.